Greetings. This is the sixth and final lecture on the Riesz representation theorem. On the previous lectures we have already constructed the sigma algebra F and the measure mu defined on F and established the outer and inner regularity properties A to C. The purpose of this lecture will be to prove the final and most striking item in the theorem, namely that the linear functional lambda is represented by the measure mu we constructed. Lambda of f equals the mu integral of f for all compactly supported continuous functions f. After we are done with this, we will also briefly discuss a version of the Riesz representation theorem for linear functionals which don't satisfy the positivity assumption. We then proceed to verify the claimed relationship between lambda and mu. This will complete the proof of the theorem. We start by a few simple reductions. First of all, even though the functions in cc of x may take complex values, by the linearity of the functional lambda, it suffices to prove the claimed equation for real-valued functions f. So let's fix a real-valued function f in cc of x. Then, as a second reduction, it suffices to prove the upper bound, namely that lambda of f is bounded from above by the mu integral of f. Indeed, if we have this inequality, let's call it double star, established for all continuous real-valued functions f, then we may easily deduce the converse inequality applying the linearity of lambda. Note that minus lambda of f equals lambda of minus f. And if we already know double star for all continuous functions, then this real number here is bounded from above by the mu integral of minus f, which is the same as minus the mu integral of f. Now, if you multiply both sides by minus 1, you find the inequality which is converse to double star. Now it remains to prove the inequality double star, and for this purpose we fix a real-valued function f from cc of x. Since f is compactly supported, its image is contained in some compact interval of the real numbers, let's say the closed interval from a to b. We will next chop up this interval into smaller subintervals. Fix some positive parameter epsilon and let rj be real numbers with indices between 0 and n. We request the following properties. First, r0 should be strictly smaller than a, which should be strictly smaller than r1. Then the remaining rj's are placed between a and b in such a way that Rn equals b, and the difference between every consecutive pair Rj plus 1 and Rj is smaller than the fixed constant epsilon. Of course, this also applies to R1 and R0. We then define the sets Aj for all indices j between 1 and n as the subsets of the support of f, where f is strictly larger than Rj minus 1 and no larger than Rj. The sets Aj are now disjoint Borel sets, all contained in the support of f and partition the support of f. In the future, we will denote this support by k. For each of the sets Aj, we next choose an open set Uj, which contains Aj and whose mu measure is no larger than the mu measure of Aj plus epsilon over n. This can be done simply by the definition of the measure mu. But we ask a bit more from the set Uj. We would like that the values of f on the set Uj are no larger than Rj plus epsilon. This can be arranged. Recall that the values of f on Aj are no larger than Rj by definition. Then, by the continuity of f, for every point in Aj, you can pick an open neighborhood where the values of fj don't exceed Rj plus epsilon. Now the union of these neighborhoods is an open set containing Aj. Finally, you can simply redefine Uj by intersecting the original Uj with the union of these neighborhoods. The upper bound for the measure Uj is of course not violated by making Uj slightly smaller in this way. Now the open sets Uj defined above form a finite cover of the compact set K. Therefore, we can select the partition of unity on K which is subordinate to this cover. In other words, we find a family of continuous functions h1, h2 through to hn such that each hj is dominated by the open set uj, and the sum of the functions hj equals 1 on the set K. Given these functions hj, note that f can be decomposed as the sum of the products f times hj, where j runs from 1 to n. Consequently, by the linearity of lambda, we see that lambda of f equals the sum of the values lambda of f times hj. Moreover, recall the formula for the mu measure of compact sets, and in particular K, which we established on the previous lecture. The mu measure of K equals the infimum of the values lambda of g, where g ranges over the functions dominating K. Now the sum of the functions hj dominates the set K. So this formula implies that the mu measure of K is bounded from above by lambda of the sum of the functions hj. By the linearity of lambda, this is the same as the sum of the values lambda of hj. We are now almost prepared to prove the inequality we claimed earlier, namely that lambda of f is bounded from above by the mu integral of f. In the coming estimate, it is worth keeping in mind that f times hj is bounded from above by rj plus epsilon times hj. Because hj was dominated by the set uj, and the values of f on uj were bounded from above by rj plus epsilon. Second, just by the definition of the set aj, the values of f on the set aj were bounded from below by rj minus epsilon. This implies, in particular, that we may define a simple function s, which is dominated by f, by setting s equal to the sum of the functions rj minus epsilon times the characteristic function of aj. Then this s is everywhere bounded from above by f, and consequently its integral is also bounded from above by the integral of f. But the integral of s can be written as the sum of rj minus epsilon times the mu measure of aj. We are then fully prepared to carry out the main estimate. First, start by writing lambda of f equals the sum of the values lambda of f times hj, using the partition of unity property of the functions hj. Next, as we observed before, the functions f times hj are bounded from above by the functions rj plus epsilon times hj. It then follows from the positivity of the functional lambda that also the values of lambda for these functions are in the same order. It follows from this and linearity that the previous sum is bounded by the sum of the values rj plus epsilon times lambda of hj. Next, we simply add and subtract something, so the value of the sum will not change. The term which we add and subtract has the form absolute value of a times the sum of the values lambda of hj. Here a was the left endpoint of the interval from a to b, which contained the range of f. To make further progress, one needs to note the following upper and lower bounds for lambda of hj. First, lambda of hj is bounded from above by mu of uj, simply because hj was dominated by uj. Second, the sum of the values lambda of hj is bounded from below by mu of k. We recorded this inequality already earlier, and it followed from the fact that the sum of the functions hj dominates the set k. We then make these substitutions to arrive at the next line. At the same time, the mu measure of uj is already bounded from above by the mu measure of aj plus epsilon over n. This was one of the properties of the open sets uj containing aj. The passage to the next line may seem a little complicated, and you may wish to pause the video to get convinced. In fact, nothing really happens here, except that various terms are regrouped, and we also use the fact that the sum of the mu measures of the sets aj equals the mu measure of k. we artificially introduce this minus epsilon here, and it is then compensated for by one of the two epsilons you see here. The other one of them is the epsilon from right here. The terms with the absolute value of a simply cancel each other out. The term with the factor epsilon over n is moved right over to the end of the line here. We are nearly done. The first sum is bounded from above by the mu integral of f. Recall that this sum was exactly the integral of the simple function s we defined earlier, which was dominated by f. The second term remains untouched and still equals 2 times epsilon times the mu measure of k. In the last term, we use crude bounds. Each of the numbers rj is bounded from above by b, which is certainly bounded from above by the absolute value of b. The sum only contains n terms, so we get the absolute value of b n times, and this n cancels out with the n from the denominator below epsilon. Similarly, the sum contains n copies of a and epsilon. The final result is epsilon times a plus b plus epsilon. The mu measure of the set K is finite, and also the absolute values of a and b are fixed real numbers whose values only depend on f. So at the end of the day, we may let epsilon tend to 0 to obtain the inequality we wanted, namely that lambda of f is bounded from above by the mu integral of f. The proof of the Riesz representation theorem is finally complete. We closed these lectures on the Riesz representation theorem rather informally by saying a few words about the so-called complex Riesz representation theorem. This version of the theorem is often at least as useful as the positive version we just established above, so it's unfortunate that we don't have time for the proof, at least for now. While the proof of the complex version would partially be based on the positive version, it also requires other concepts and tools which we have not yet introduced. The positive Riesz representation theorem only dealt with and characterized linear functionals lambda on the space Cc of x, which had the additional property of being positive. If f is a non-negative function, then lambda of f is a non-negative real number. What can we say if lambda fails this assumption? One thing is clear: if lambda fails to be positive, then it certainly cannot be represented by a positive measure, or in other words, a measure mu defined on a sigma algebra f, which only takes values between 0 and infinity. Indeed, every functional represented by such a measure would automatically be positive. Under mild additional assumptions, it turns out that not necessarily positive functionals lambda can still be represented by complex measures. By definition, these were complex-valued set functions defined on some sigma algebra f, which are countably additive on disjoint sets, and assign the value 0 to the empty set. It is worth emphasizing separately that a complex measure is not allowed to take the value infinity. Complex measures will be discussed more in depth in later lectures. In order to state the complex Riesz representation theorem, we need one more definition. This is the definition of the space C0 of x. As usual, let x tau be a locally compact Hausdorff space. If f is any function defined on x and taking complex values, we say that f vanishes at infinity if for each positive epsilon there corresponds a compact set K such that the absolute values of f are smaller than epsilon outside this compact set. It is clear, for example, that every compactly supported function vanishes at infinity, since the values of such a function are simply 0 outside the compact support. Now the space C0 of x consists of all continuous functions f defined on x taking complex values, which vanish at infinity. Evidently, the space Cc of x, which we have been working with until now, is a subspace of C0 of x. We want to couple the space C0 of x with a suitable norm, and that norm is the subnorm. Recall that the subnorm of a complex-valued function f is the supremum of its absolute values. It is not hard to see that the subnorm is finite for all functions f in C0 of x, and in fact the pair C0 of x coupled with the subnorm is a normed space. Actually, it even turns out that this couple is a Banach space, that is, a complete normed space. We leave this as an exercise. There is a clear relationship between the spaces C0 of x and CC of x, which will be part of the same exercise. Namely, the space C0 of x is the completion of the space CC of x coupled with the subnorm. I'd suggest that you pause the video now and think for a moment. Why isn't the space CC of x already complete under the subnorm? And if you have a Cauchy sequence in CC of x under the subnorm, why does the limit function still have the feature of vanishing at infinity? As a final reminder, let's recall what it means for a linear map lambda between two normed spaces m and n to be bounded. This means that there exists a positive constant c such that the norm in the space n of lambda of x is bounded by c times the norm in the space m of x for all vectors x in M. The complex Riesz representation theorem will characterize all bounded linear maps between the spaces C0 of x and the complex numbers. For such maps lambda, boundedness means that the absolute value or complex modulus of lambda of f is bounded by c times the subnorm of f for all f in C0 of x. Here comes the statement of the complex Riesz representation theorem. Let x tau be a locally compact Hausdorff space, as usual, and let lambda be a bounded linear map between C0 of x and the complex numbers. Now you can already see that the assumption of positivity has been traded for the assumption of boundedness. And of course the function space is also a bit different. Under these assumptions, the conclusion reads that there exists a unique, regular, complex Borel measure mu on the space x, which represents the functional lambda in the usual way. The value of lambda at f equals the mu integral of f over x for all f in C0 of x. As we mentioned before, we don't give a proof of this version of the Riesz representation theorem, at least yet. For a reference, see Rudin's real and complex analysis theorem 6.19. If you look closer, even the statement of the theorem contains a couple of points we have not properly defined. What does the integral with respect to a complex measure actually mean? And what does the regularity of a complex Borel measure mean? Both of these are non-trivial questions, which we will discuss later on the course. Actually, the meaning of regularity is easy enough to mention right away. A complex Borel measure mu is called regular if the so-called total variation measure, denoted by mu with absolute values, is regular in the familiar sense we have discussed before. But the definition of this total variation measure will have to wait until later lectures. This completes the lecture series on the Riesz representation theorem. Goodbye for now.